Today we're going to start our learning seminar with Christian Haase, who's going to teach us about lattice polytopes. Thank you.
All right, yeah. Well, thank you for the opportunity to speak here. So I'm scheduled for 2 talks, one today, one on Thursday. And I was supposed to tell you something about lattice polytopes. And yeah, so I have a problem with decisions. So so my plan is that I'm going to machine gun a lot of notions and theorems and examples to you today. The only purpose of this is kind of deciding what you really want to hear about, and also gauging a little bit what the background is. So the question policy is. So if something I'm saying, thing that I'm saying you don't understand, please ask. If I'm saying something you don't grasp, like how is this possible, or is this something you want to know, you really want to know, take a note, because it's going to be on the test at the end. Right? So at the end I have a little test, and what your task is to have 1 or 2 topics that I mentioned that we will then discuss and decide on what we're going to talk, what I'm going to talk about on Thursday. So here's my invitation to lattice polytopes. I have a chapter 0, which is a setup. So capital P for me always is the lattice polytope. Which is take integer valued points, which I call lattice points, bunch of them, and you take the convex hull. This would be a good opportunity to ask, what is the convex hull? So when we ask it, it's going to press on. Okay. So my running example of a lattice polytope is the interval of length 3. That's also a really nice lattice polytope. The other main player is a rational polytope cone. Which means it's the lattice points for us. We work in the lattice M. Often we'll just take B to D. D is my dimension. And a rational polynomial cone, often I will write as the conic hull of n vectors, all n. I might also write this as D by n matrix. Just take the cone of that. So what do I gain from this? From this cone, I get a monoid intersect M. Like here, this is a beautiful rational cone. If I take 2 lattice points in here and add them, I can still get a lattice point and still stay in the cone. Then my group has a unit. This may be our first little theorem. It is finitely generated. So R, capital R, is going to be little k is the field, and the monoid algebra, this is finitely generated. Hey, questions? Okay. So I'm saying this is finally generated. Yeah. If I pick a set of generators, which I will write as the matrix, as I said, as a defined matrix. If I choose such generators, that gives me a presentation. This algebra, each x goes to one of the generators. And there's an ideal here, which is called Lord. Toric ideals are one possible topic that maybe haven't. So I do have a topic on the list. What we could learn about. So, these are the main players. What is the connection between P and C? Is what I can do is I can take my polytope, I can add a dimension, or add a row of ones to my generators if you want. Take the cone of this thing. This is something that I've done here. This is the cone over my running example. Interval of length 3, I've listed it to height 1. And then look at the cone. And this gives me a natural grading of the ring. Okay, so in this case R that's positive. Grading, the beauty is if this is P, then the degree 2 P's is 2P. Degree 3 P's is 3P. So here comes our first actual theorem. R is going on.
Actually, by 2p, what do you mean in this case?
A times P, so P times X. But really what this is P times the 2P times. This is the dilation.
Yep.
More questions? Oh, before I press on, I already apologized to some of you. I apologize to the rest that I made you all bring graph paper. I don't have as much audience participation as I wanted before I started preparing. But maybe if you have never done this, let's spend 2 or 3 minutes to try to write down this toric ideal with this polytope. Take some notation. The generators are these that I want to pick on these 4 dots here. They get variable names. I call them A, B, C, and D. And let's just see, like, what does the relation among these?
A times C is B squared. Oh, we're not always close to it here, I'm so sorry. Pardon me.
We'll talk later.
Sorry.
I mean, have. Who has found the relation? Who has not found the relation? We're tough. Okay.
I don't know if we found all of them. And
That's a good question.
I don't know if people on Zoom can hear us, so maybe you could repeat the questions.
I can also repeat the question.
Yeah,
I mean,
that would be. I will.
so Fruit in the back asked, how do we know that we found all the relations?
I will
Presume,
say a few things, and that's one of the possible topics. So you have found a relation, have you?
A C is B squared.
So, sorry, what?
I couldn't hear.
Oh, sorry, Mike. A C is B
So
squared.
this point here, I can write as a, well, this is just this point twice, b squared. But it's also this one plus this one. Okay. And I mean, the same game I can play here, right? So if I take c twice, and I get c squared, is the same as bd. Round. Looks good. So this one also has relation. I can either add b and c here to get here, or I can add a and d. So a, d, minus b, c. Probably all have seen this ideal before this twisted here. Okay, so just to get a little bit of a feeling of what we're talking here, you also see, I mean, I've written this a little suggestively that everything is really multi-graded, right? I don't have just a grading like this. I can generate this ideal by elements which have labels, which are labeled by lattice points here. So this whole thing is multi-graded, and that's also something we can talk about on Thursday. So here are some more results. If it's Cohen-Macaulay, then I can write the Hilbert series. Now it's graded as the Hilbert series. I can write the Hilbert series as a rational function, which is usually the numerator is usually noted by H star. And H star really the Hilbert function. are divided out for regular sequence. And this is more problems. Okay. That's something.
Sorry, can I ask a quick question? So the theorem you wrote, R is cone Macaulay, is that R specifically for cone that you get as a cone of a polytope or for any cone?
Any cone.
Any cone. Okay.
Then, in the half-grade ring, of course, I look at the toric right. Well, this is the projective toric righty.
By the way, are cones always pointed? Or do you not care?
I think I want them pointed here. Yeah.
I'm so sorry, pointed means strongly convex.
Yeah.
So the same thing, synonyms?
Yeah.
Thank you.
Pointed and strongly convex are synonyms.
Yeah. So here I'm actually sweeping a few subtleties under the rug. They're gonna be mentioned a little bit in chapter 2. But let's just say where the polytope really gives us a variety plus line the polarized variety, and about this we also know a few things. So it is also corollary. So the degree of this line bundle, well, H star valued at 1, of course, and that's D factorial times volume of P. I will call the normalized volume and indicate by capital V. That's a much nicer volume because it's always an integer. And another theorem. NP is smooth if it only is for all vertices of P. We have that if I take P, I shift P so that D becomes the origin. And then I look at the cone, it's isomorphic. Which reminds me, I haven't talked about isomorphism, which I had intended to do. So the lattice polytope, okay, this one, is only really well defined. All the notions we look at shouldn't depend on what coordinates I put on my lattice. So, you know, this and had I drawn this more properly, these would be the same polytope. Okay, so something that takes some getting used to is, and I'm going to talk about distances in this setting, but really these two lattice points here are the same distance apart as these two lattice points. These are isomorphisms. Like this is a lattice basis that can reach every point by interlinear combinations. This is a lattice basis. So really, in terms of my distance is always normalized so that the smallest lattice thing is distance 1. And similarly, these two hyperplanes here are the same distance apart has these two angles. There's no lattice points. Okay. That's something I wanted to say. So up to this isomorphism, that means I have a lattice basis at n vertices. So the little square there is fine. If I take this lattice polytope, not fine because I take this vertex, then there's no way I can reach this lattice point as an integer linear combination of these two. It's the middle, I need coefficients that have that. This is not so good. And also another thing, the vertex of this thing is contained in D facets, D inequalities. So this is a simple polytope. That's another thing that.
So your isomorphism is essentially only elements you see, your.
Yeah, it's like-
mixes of those.
With integral inverse.
Yeah.
So- All right, so that was the setup. Number one is counting. I don't know who did the homework. Just to show that already dimension two things get a little bit more complicated than thing primarily. So, did anyone look at this
It's
and did you realize everything?
not everything.
What do you mean this is?
This is in the Zuluk channel.
Oh, I didn't see.
We probably should have also put it in the email. But okay.
Okay, so I have a polygon.
Do you have a printout of that? You don't? Okay.
I have a polygon and it has normalized volume A, that's an integer. It has a number of boundary lattice points and it has a number of interior lattice points. Right? Then these numbers satisfy an equation. I call the equation I call P because it's zero, 1899. Right, so any two of them determine the third. And then you can ask the question. If you have three numbers, where do they come from? Poly. Well, if it only is. Wait, big holes and. I there is 0. And B is at least 3. No interior lattice point. I can draw a really long triangle without drilling any lattice points. Or I is equal to 1 and B is between 3 and 9. This could be an obvious observation, right? To figure out these, or I is at least 2 and 3 is limited. Fine, well, things. Like in I equals 1, here you would get 8, but in fact, That's kind of the solution to go. So already here, I mean, we have a full answer to this question, but, I think it's already more. Uh, uh, More interesting, let's say, than.
So on the homework, you had written the example 524, so that should that be impossible by this?
I think so.
Sorry, what did you say?
Sasha, say it louder.
Sorry, on the homework, Christian had included a bunch of triples of these A, B, and I. One of them was the triple 524, which I guess we should see as impossible by the theorem. So there should not be a lattice polytope which realizes the triple 524.
Why? Is this the same order?
I think so.
Oh, no, actually, no,
Five,
it was
four.
BIA.
Oh,
Yeah.
is it?
Oh, my God.
Oh, yeah, it is. BIA.
I was like, I drew 524, so I don't know.
Yeah, so this should be followed. But there should be one example where which conflicts this,
Yeah.
hopefully,
What do you mean, one example contradicts that?
on the homework.
Is it,
So.
There was one
trying to
impossible
show
one
that
on the
there's
homework.
non-example, or one non-example, not that. You have
There
an
was,
expert.
there was one hopefully that contradicted this equation, and then there should be one example that. Okay, let me put another question. In a similar vein.
I'm looking on Zoom, but I do not see.
it's in the, I think it's in the seminars channel. And then there should be, that's right, it should be before Mahrud's announcement. So Christian made it.
Oh, I see here.
Here's another precise question. Which you do not know the answer to. Is there a lattice polytope with this H star vector? Okay, from this H star vector, we can read out a few things. So if the polytope is three-dimensional, doesn't have to be, could be high-dimensional, but then if the polytope is three-dimensional, it will have three interior lattice points. It will have 71 lattice points. So it will have a certain volume, which you get by adding these numbers. And we don't know if this is possible. 73 is possible.
So the way that this translates, so the largest one is going to be the number of interior points in general, or it's just.
If you have interior lattice points, yes.
Okay, but
Well, yeah. So then it's equal to the dimension, otherwise, that's something we can talk about
yeah, let's go.
on Thursday.
This one's really not known.
This one's not known. So. So I'm going to look at all lattice polytopes in the vector space. So that the volume of E is bounded by some number B. That's the big set, but then I'm going to look only at equivalence lattice on the whole. Lattice basis changes. Then theorem, I get a finite set. And if I look at the number of digits of this number, I can tell you how fast it grows. It grows just barely not linearly. The And in particular, if I bound the volume and the dimension, then there's a finite number of equivalence classes. There's a bunch of these finiteness theorems. I fix the dimension and I fix a positive number of clear lattice points. Then the volume is also bounded.
I'm
This
so,
shows that I equals 0 does not work.
I'm so sorry, what was CFD? CFD.
Some constant that only depends, oh, maybe I should call it C because C is a constant. Maybe I call it little c.
Some constant depends on D, okay.
And what, so we're just assuming P is any lattice polytope that matches the guy.
Yeah, that's good point. If P is smooth. And about the number of lattice points. I guess, yeah, sorry, fix D again. Then there's a finite number of smooth lattice polytopes with a given number of lattice points. Okay, so here's another important example. Take the unit square in R3. And then you take this point, this point, this point, and then you take the point 1, 1. And you lift it to really high height. It's a beautiful tetrahedron. Okay, that's a tetrahedron. It contains how many lattice points? 4. No matter how high I lift this, the height of this point is essentially the volume. So these are all different, but they all have the same number of lattice points. Without the smoothness, it's horribly wrong. This smoothness assumption. This is true, and I was going to give you numbers, but in view of time, I'm not going to give you numbers. There's classifications. So for D equals 3, for D equals 3, these for I equals 1 and I equals 2 have been classified. It's like 22 million. That's 600,000.
And are the numbers known for us once, or at least some way of calculating?
I don't think, like in dimension 2, things are known quite a bit. In dimension 3, what I said is kind of the state of the art. In dimension 4, nothing. This problem, there's a classification. It's recent, it's kind of ongoing, and it's going to tell me that I can now classify it up in dimension 3, smooth with up to 50 lattice points. Previously, this went up to 14. Now just up to 16. And let me give you one more example just to tell you a little bit about this CFD here. So I'm going to define the Sylvester sequence, which starts out with 2, and then the next is just the product of the previous ones plus 2. Right? 2, 3, 7. In fact, and bounded below by 2, 2, and then minus 2. This thing grows fast. So
Sorry to interrupt, Christian. I think you somehow muted yourself. All right.
We just left the audio. Okay.
you hear me now?
Yeah. Okay. I can hear now. Yeah, that works. Thank you.
All right. So,
So what did you call that sequence, that beautiful one?
Sylvester sequence.
Sylvester sequence, thank you.
So if you have two binary random variables, then they have together 4 states that they can take, and if you have a probability distribution of these 4 states, that's a point in the tetrahedron. And on this circuit, if and only if the 2 random variables are independent. So that's another topic that we could potentially talk about Thursday.
Now, a second, which dark surface did you say that was? The one.
The unit square.
The unit square, right, okay.
And the positive points actually map back to the polytope, that polytope.
Hey, what do you mean by positive points?
Well, it sits in a projector space. You look at the
This is-
real part, and in the real part at the positive points.
So like if you're taking the field to be R and then you take like the non-negative points there. Yeah.
The points.
Projectively, all the signs are the same. That's what it.
So points where all coordinates are positive.
Yes.
Statistical.
Yes. And this map is the mode map.
Yeah.
All right, so yeah, time is flying, and I'm only at chapter 2.
How many chapters are there supposed to be?
What?
How many chapters are there supposed to be?
I guess 3.
Well, then there we go.
3 is a little bit of a. Thanks. So, having lattice points, so if I have a lattice polytope, And let's make it general from the beginning. Let's say we have another lattice polytope in the same space called Q. And then take last point. And then take one from each. If I add these two lattice points, I'm still gonna have a lattice point. And not just a lattice point anywhere, it's the sum of 2 points in one in P, one in Q. So that set may cost me some. So it's gonna be a lattice. In P plus Q. So in general, studying this map is very interesting. In particular, the question is, when do I get all the lattice points? This can be already interesting if P and Q are the same. Take this tetrahedron up there, then this map is not different. Okay, and so looking at this, we get hide this from you. Sorry about that. Let me put the hierarchy here, at least part of it. So if you look at this picture here, this was the subtleties I meant when I talked about trying to define the projective toric writing. This monoid here, points at type 1 really are generating monoid. If you play the same game with the tetrahedron over there, that's not true. Okay, so the question whether this map, if I take it from P to P, and then from 2P to 3P, so if I want to know if every last point in K times P is the sum of K last points in P. That question has many names. That is an indication that it's an important question. So let me call this R if generated by R1, standard graded,
Christian, sorry to interrupt again. Somehow the mute got turned off again, or turned on again.
Yep, someone's coming into the room.
Okay.
I think perhaps when you hit the camera over there, that happens. I don't know. I noticed
Yeah, it's working again. I don't know if there's something over by that camera when you got over to that corner. But it's okay.
Question, could you just, I'm so sorry, the IDP, could you say again what it stands for?
integer decomposition property.
Thank you, thank you.
So in particular, what this implies is that the light bundle is very ample. So this really is an embedding, and the embedding is such that if you look at the affine cone, the origin, the singular, definitely singular point, is normal. So this is one important property, and
Wait, sorry, I got confused. Why is the direction of the arrow going up?
if you have the IDP, you're very ample,
If you have the idea.
not the other way around. But if you want, I'll show you an example.
I think it's just that if you have a projectively normal line bundle, then you must have, it must have had an embedding. So,
That.
so
Okay.
yeah, that part of it is, yeah. But not everything that's very ample is projectively normal, so certainly the error.
So. This IDP, for example. I can guarantee, for example, in dimension 2. If you have a polygon, you can always triangulate until you can no longer refine. And then by Fick's formula, all these triangles are essentially lattice spaces. So in dimension 2, you always are predictably solved because something stronger is true in dimension 2P and a unimodular triangulation. And these simplices, which when you list them to like 1 are lattice spaces, these are called unimodular simplices. And of course, if you have a covering even by these, then you have the instrument composition problem. And there's a whole hierarchy of different properties. This one does not have a really good correspondence in computed algebra.
Doesn't it imply causal or something like this?
I wasn't gonna put down the entire hierarchy here, but so some triangulations are regular in the sense that it can fold them upwards, like it can look at these things as folds all in the same direction, and it kind of works. And if I have a regular unimodular triangulation, that's equivalent really for the toric ideal. That's very initializing. Right? That now is an answer to the previous question, like from the very beginning. How can I tell that I'm done with the generated Freie? If you have such a regular unimodular triangulation, you can read off the Gribner basis from the triangulation. Okay. So here, in this example, if I subdivide this polytope into these 3 segments, that is a regular unimodular triangulation. Right? And how do I read off the Gribner basis? I look at the non-faces of this triangulation. Okay, so A and C, for example, do not form the face. Well, add these 2 you get here. Look where this point ends up. This point, because the unimodular triangulation, this point you can write in a unique way, just using vectors from this support. That's your trailing term. Okay, so I start with the non-face, that's the leading term, so that gets underlined. And the trailing term is supported by simplices of the triangulation. AD is a non-face. You add A and D, get here. That's the underlying term. Go back. You find a point which belongs to this simplex. So you can write this point as an non-negative interlinear combination of these vertices, that's the Freie term.
You're saying that P can have a unimodular triangulation that's not necessarily regular.
Absolutely. I can give you an example of this.
So then what you said, Chris, like, what's necessary?
Yeah.
Consul would be here, like,
Yeah,
here the
that
minimal
is
non-phases
but not
consists of
modular.
only two elements.
Yeah.
That- So for example, the Birkhoff polytope of 3x3 matrices does have a beautiful regular unimodular triangulation. But the ideal is this hypersurface is generating degree 3. Just not. You need degree 2.
I suppose if you're just, you don't even need it to be a decomposition, as long as you're just covered by polytopes as IDP. We have IDP.
Yeah.
It's-
But for the causalness, you need a quadratic
You
group.
need the whole ideal.
You need this plus the quadratic.
Yeah.
The generated. Then you're running perturbated. So. Here's a bunch of conjectures. Let me go as far as saying a bunch of ridiculous conjectures, but still I have to say to you. If P is smooth, then it has the IDP.
Actually, what is IDP mean? Is that easy to say? What is it?
Integer decomposition.
It's like every last point in K times P is a sum of K last.
Oh, I see.
If P is smooth, then the ideal is quadratic generated. If P is a matroid polytope, I didn't tell you what it is, but I couldn't tell you Thursday. Then this is what I.
Do either of those first two imply each other?
No. Look. Somehow for me, this only really makes sense if this is true. But you can still ask it without this extra assumption. They're wrong. But I mean, for some of them, even if you had me the counter example, I wouldn't know how to show it together.
Wait, sorry, what? Again, if I give you a counterexample, you don't even check.
Check me as present. Here's a polytope. I promise you, it contradicts this conjecture. Then what would I do with it?
I see, so I have to.
I want to be famous, right? I want to publish this example, and I want to show it's a counterexample.
Wait, sorry, if I give
So-
you polytopes, when you compute the ideal,
Oh. Like for a reasonably sized polytope.
okay.
So there are no known counterexamples to these. You just think they're probably not.
I often call them conjectures. They're not
Okay.
disproven yet.
But you would rather conjecture maybe that
Maybe
They're all
this
false.
is White's conjecture, maybe White's conjecture. Yeah, that's false.
Also, sorry, since the H star came in, you did not tell us how to compute the Hilbert, the numerator,
No,
right?
that will be topic of this.
Okay.
Just let me mention. We're not just talking about generators. We can also talk about high energies. I hear that some people have worked on their laser surfaces. There is recent progress on this front via simplest model. Said this whole shebang is multi-graded, and so you get refined multi-graded Betty numbers, and in each fixed multi-degree, the Betty number you can write down the simple complex, and the Betty numbers are the simplified homology of this. How much time do I get? Not at the how much time can I get?
We don't have an afternoon talk today. If we go late, a little late for lunch.
It depends on who uses this room.
Oh, that's very true.
Actually, Adam might know.
Until they kick us out.
Adam, do you know how long we have this room for?
No, I don't. But Tuesday there is a class in that room.
Lynn
Sometime.
might.
So you guys scheduled it until 12 p.m. today for the morning sessions.
I see.
But if there's somebody else
There's
as well.
Is there something else happening immediately after? Do we need to clear out?
Let me just check.
When is the seminar?
I've had to cancel.
It's
1:30?
well, it's supposed to be at
1:30,
1:30, but they told us that there's a class scheduled right at 2:30, so they would like us to move it ahead.
At the moment, there's no class after 12 today.
Okay,
So-
is it okay if we stay in the room then for a bit?
Yes, for this session, yes.
Well, it hasn't, I think it's happening today, but I'm gonna change the time.
Well, that was today, you don't.
Okay, so. How much time should we give Christian?
2 more minutes,
So
because that's what we all scheduled for.
Let's say, if anybody needs to leave, you can leave, but then I'm very curious to hear more about the sphere symmetry, so I'll stay here for another 10 minutes.
Yeah, let's.
Let's go. All the way around, we are going to finish like at 1. Go.
An umbrella headline for various topics which I want to at least mention. So this is a Cohn-Macaulay ring. If I look at the lattice point in the interior of the cone, that's a module over that ring. And this is the canonical module of R. So or is Gore's chain. And only I can get. Well, right in here. I can get this set of lattice points by just taking all lattice points and moving them by one generator. This happens if and only if it doesn't come from. Sense that you can read the coefficient sequence back and forth. The same thing. Again, there's classifications. So let me just mention in view of time, let me just mention a few key words. So there's the reflective polytopes. which is a special class of these Gorenstein polytopes, those that have an interior lattice point.
Sorry, the theorem is
I'm
that
sorry, the theorem is what? Sorry, there's a left, is there?
Ours Gorenstein and only if H
Oh,
star.
thank you. I was missing the
Wait, so
left-hand
this-
side, sorry.
This condition doesn't mean that there's a, that says that there is a interior lattice point.
No,
No, it doesn't say that at all.
so
I'm sorry, Michael.
if the degree of U is 1, then there's interior lattice point, and then P is reflective. And otherwise, P, some dilation of P will be. It's another equivalent I could put here, but I didn't define what reflective is. It would be a topic for later. And then there's also something like, which I would call minimal model program, flat adjunction theory. Which really in the polytopal world amounts to take your polytope and you start moving the facets either independently or if you do adjunction theory, well, actually, yeah, you move the facets at the same speed inward. You get pictures like this. No, this grows, this edge gets shorter and shorter. At some point, an edge contracts. That's called the net value then. And then you get shorter and shorter, and at some point, the thing goes away entirely. That's the what is it? There right now.
there was a real contraction.
It's a negative.
First one, it's
Negative Kodaira energy. It's the super effective threshold here. And you can say things about polytopes using these techniques. Using these techniques as well. So this is the list of topics I had prepared for today. I would, for the sake of time, I would like you to use your devices, maybe scan, if you can scan this QR code there.
Not working, I can also put it on Zoom. Yes, thank you.
So there's one question, it's multiple choice, just click on a few of these which you found interesting. And there's 2 more options for adding free text topics that I would like to.
When would you like the answer to this by? Like, is it okay if we think about it and like fill it out later today, or do you want to go right now?
Yeah,
I'm not gonna adhere if it's like. Well, I will take this into consideration, the result.
Okay.
so just to be clear, if in case anybody didn't hear, for the online people, fill out the poll as soon as possible. Christian will take into consideration the suggestions
That's right. And
as they trickle in.
as they trickle in, exactly. I will, of course, sometime today would be nice so that I can prepare. And whoever's here, I would love to discuss more, get a feeling of what people know, what people want to hear. Yeah. So I just wanted to get this out so that everyone can answer these.
Okay, so let's call it the official end. Thank you, Christian.